let's get to it. So, we last time we saw that there was a suspicious similarity between the p-test for series and the p-test for integrals. Okay, and so what we want to kind of do is talk about why that worked. And okay, so let's just recall. Oops. That what was the result from before? We had that the integral 1 over x to the p converged when p was bigger than 1 and diverged for p less than or equal to 1. Okay, great. We also said last time that basically the same result was true with series. Okay, is that really all that surprising in some sense that they ought to kind of behave similarly? I'd argue no, because what really is an integral? It's a special kind of series, right? It's a series where you've let some stuff go to zero, but a series and an integral are kind of the same flavor. Okay, and so that brings us to what's called the integral test. Okay, so let's suppose that I've got a function and I also have a sequence, and the sequence and the function agree um, when I put in a whole number, right? So this would be like f of x equals x squared versus a sub n equal n squared. They're kind of the same thing, but I'm thinking of one of them as a continuous function, and the other one is only operating on whole number values, okay? So, and I want them to agree on those whole number values, okay? Then the two things do the same thing, okay? Meaning that if one of them converges, the other one also converges, and if one of them diverges, the other one also diverges. Okay, so you can't have the situation here where one converges and the other diverges. If that happens, then you mess something up. Okay, so let's look at a quick example of that. Well, we looked at this series last time. Okay, what was this thing called again? This particular series? Harmonic series, yeah, good, okay. And we proved last time that it diverged by using Arem's clever trick, right? With the grouping up every power of two terms and then collapsing them and so on. So we already know that this thing diverges, but let's prove it using the integral test. Okay, so if this is generally how this is going to go. You have a series you want to examine, turn that into an integral, and if the integral, like the only time you would want to do that is if the integral is something that's reasonable to compute. Okay, so what we'll do is let's consider the integral from 1 to infinity of 1 over x dx. All right, so I turned the series sort of into its corresponding integral, and then I'm going to work with this integral and see, does this thing converge or diverge? Okay, now in this case, we already know, what should we get here? That integral does what? It should diverge. Okay, for a couple reasons. One, we already know that the series in question diverges from last time. Also, we could just say the p-test for integrals here. But let's pretend that we didn't remember any of that. How would I approach this if I forgot the p-test? Well, I'd have to first, it's an improper integral, so I need to think of it as the limit of a proper integral. What's the antiderivative of 1 over x? Natural log. Okay, and then of course, what's the natural log of 1, Kim? So I don't have to worry about it. And so I'm taking the limit here as a goes to infinity of log a, and what is that? That's a big old plus infinity. Okay, so the integral that we were examining diverges. Okay, all right, so are we Gucci with that part? Okay, in this case, yes, I've gone into more detail as to why it diverges than perhaps necessary, because we already knew the result, the p-test, right? But this would be basically, what about if we forgot the p-test kind of thing, okay? All right, so if the integral diverges, what must be true about the sum? It must also therefore diverge, okay? They do the same thing, whatever that is. All right, and so hence, okay, so, but we already knew that it diverged because we proved that last time a different way. It's always nice to know that there's more than one way to skin the cat. If we were playing the Bell game this year, we would hopefully discover that. Yeah, unfortunately, we're not. So those evil Dannies get to keep the Bell for a free year, not having earned it. I think what we should do is that the Bell should be placed in neutral territory for the year. Well, yeah, but by neutral territory, I mean like a bank vault or something. Yeah, I don't know, but would that technically therefore be a bank robbery and hence the feds would get involved? Seems like a bad idea. No, because that's not a bank. It was, yeah. And they almost got away with it. You know what got the campus police officers' attention down there? The getaway car had its lights on, and he was like, "This is a little weird." And so he was just like, "I'm just gonna watch and see what's going on." Yeah. So had that not done them in, I think the pressure plate probably would have. But um, anyway, okay. So Right. So we already knew that thing diverged, but that's okay. All right, good. Um, Now, a warning here. That the integral even if so let's say that they both converge. Just because they both converge, that doesn't mean that they converge to the same number. Okay, so I have to emphasize that. Let me give you a good example. Okay, so why don't you guys take a minute and figure out what this integral is? 1 to infinity of 1 over x squared. What does that converge to? And I'll take the series. Okay, you guys do the integral, I'll do the series. Need to put on the Jeopardy theme music. That would be awesome. Yeah, I'd be rolling in streamers, subscriptions. Yeah, I got the bots that are, trying to sell me subscribers, and had to ban 2 of them this morning in computer science. Yeah, but they were spamming the chat. So, banhammer. So, to what if doth thy integral converge? Okay. Mr. Trapp, any suggestions? What does the integral converge to? 1. Jack, do you agree? Any disagreement? That's what you had, right, Cole? Well, first write it as x to the minus 2, and then the integral is x to the minus 1 over minus 1. Right, power rule. Minus 1. Minus 1. Okay? All right, so that converges to 1. Great. What does the series converge to? Trust me, I'm a doctor. Okay, it converges to pi squared over 6. Now, where the hell did that come from? No? I mean, it's kind of like in Monty Python, right? The Spanish Inquisition, right? Nobody expects a Spanish Inquisition. No. Okay, so I am being a little bit coy here. Why is that pi squared over 6? Well, you guys need about 3 or 4 more classes to see that. Okay, so if you take a partial differential equations class and you learn about Fourier series, then you can eventually show this. Okay, but until then, you'll just have to trust me. Okay, now, last time I checked, those two numbers are very different, right? So my point is that just because they both converge does not mean that they converge to the same number. And in fact, that almost basically never happens, that they converge to the same number. They just both converge. And like I said, I mean, this is a little bit unfair for me to pull a pi squared over 6 out of thin air, but you'll forgive me, right? No? Okay. All right, so good. Now, we haven't proved the integral test, and I'm not really going to. We'll kind of tease out a proof maybe a little later. But the proof depends on the comparison theorem. Okay, so let's think back to integrals. Let me say it this way. All right, so if I have two functions, and I have to be careful here, this is something I messed up on the one of the assessment questions. I forgot to state it formally. The functions have to be non-negative, okay? Because what could happen with an integral, for example, if you've got a function that's both positive and negative? Well, places where the function's negative, the integral on those parts does what? It can cancel out stuff where it's positive, right? So we could have a function with some, like an integral of sine or something, where the integral might be 0, and we get gobbledygook if we include the negative. So the two functions must be non-negative. And let's just say that f is always less than or equal to g on some interval, okay, from a to infinity, whatever a is. Oftentimes that's 0 or 1, but it doesn't have to be 0 or 1. It could be just any constant. Well, if one function is smaller than the other, and they're both positive, then the integrals of them should obey the same relationship, right? If f is smaller than g, then the integral of f ought to be smaller than the integral of g. That makes sense, right? Because integral is about area under a curve. All right, so point one, what happens if the, quote, smaller integral diverges? Well, then what's the bigger one got to do? It also has to diverge, right? And on the flip side, what happens if, what am I going to write for the second case? Which one is it? If this, well, no, that was for the integral test. If the bigger integral converges, then the smaller one must too, right? Because it's less than some convergent, some value. I'm sorry. You said, shouldn't they do the same thing? Yes, if the bigger one converges, then the smaller one converges. But if the smaller one converges, you can't say anything, right? Because everything is bigger than a every divergent series is bigger than every convergent series. Doesn't help, right? Okay, so does that ring a bell? Ding ding. Well, if this works for integrals, and we have the integral test that says a given integral and a given series that are sort of twins do the same thing, then could I go through here and replace all of the series with integral, or I said that backwards. Replace all of the integrals with series. Yeah, I could. Okay, so that was the integral test, the integral version, and the series version would be basically I'm going to replace all of the series with, or the integrals with series. Okay, so I'd say if 0 is less than a sub n is less than b sub n, for n greater than, say, 0 or 1, whatever, then the series, this series is less than or equal to that series, and if the first one diverges, so does the second. And if the second converges, then so does the first. Okay, so exact same thing as the integral version of the comparison test, but I've just basically done a control F and find and replace integral for series. Control F does finding, and then it pops open a thing, and you put in what you want to replace with, right? Or Apple F if you're an Apple guy. Command. Yeah, it's control on PC and Linux, but command on Mac. And as somebody who uses all three, it's sort of funny. I don't mess it up. My fingers just go to the right place. Yeah, I'll explain later. Yeah. Mac OS is Unix based. So is Linux, in a sense. But okay, so the series version works very much like the integral version. The tough part here is that usually you have one of the two sequences, either A sub n or B sub n, and it's up to you to pick the thing to compare it to. Okay, and we saw that when we were doing the integrals, right? You only were given a single integral, and you had to come up with the other dude to compare it against. All right, so let's look at an example. Am I good to move on to the next sheet? Are we Gucci? Yeah, okay. So let's look at an example. Let's consider, say, n squared plus 1. Okay, now you could do this, by the way, with the integral test, because what's the antiderivative of 1 over x squared plus 1? Arctangent, right? So you could do that and go that way. But let's do this with the comparison theorem, okay? So I only have one given series here. So what I need to do is I need to choose another given series, or another series. I need to argue that the inequality goes the correct direction. I need to argue that I have two non-negative series, and then I need to apply the theorem, okay? Now, in this case, 1 over n squared plus 1, that's always non-negative, right? Because I've got the thing in the denominator is always positive, so I don't have to worry about that. What do you think the natural thing to compare against here would be? 1 over n squared, okay? So let's consider do they go in the correct order, right? Meaning that well, first off, what do you guys think 1 over n squared plus 1 does? Do you think it's going to converge or diverge? Just gut. Converge. It's basically 1 over n squared, right? And that plus 1 is going to kind of throw a wrinkle in this, but we should expect that it's going to converge. That's why I wrote the inequality in that order. Is that inequality true? You think so? Okay. Why is it true? It is, I promise. Okay. Mm-hmm. Right. Bigger denominator, smaller fraction. QED. Right? And why are both of these things bigger than or equal to 0? Well, what kinds of numbers are we dividing by? Positive numbers, right? So we're not going to have any negatives here. Okay, so you guys buy that? Yep, all right, so that's true. Well, I need to know what that second series does. It either converges or diverges. What does it do? It converges, okay? Why? Okay, good question. So the 1 over n squared goes to 0, right? But just because you've got a sequence that goes to 0 doesn't mean that that series converges, right? That's the trap that you could fall in, yeah, from Friday, right? So just because the sequence goes to 0, that doesn't tell you anything. It tells you jack shit, no offense, Jack, uh, about whether or not the thing's going to converge. However, if the series converges, then the sequence goes to 0. Okay, so what was it called when you conflate P implies Q with Q implies P? That's called, what if I've got a logical statement, P implies Q, what's Q implies P called? Nope.
Next positive is the one that we want.
Yes, not P, not Q implies not P is the counterpositive. Nope, that's not Q implies not P. P implies Q to Q implies P is called the, come on, Will, you're wearing them. Converse. Oh, you're not? Okay.
I was wearing them last time.
You were on Friday, though. All right. Okay, the converse. Okay, so conflating P implies Q with Q implies P is what we call the converse fallacy. Okay, and you guys fell for it left, right, and sideways on Friday, right? No, it's just that conflating a thing with its converse is the converse fallacy, right? Sometimes they are equivalent. For example, let me give you a statement that is bidirectional. In a right triangle, the sum of the squares on the legs is equal to the square on the hypotenuse. Facts, right? If you have a triangle and it just so happens that the sum of the squares on 2 of the sides equals the square on the third side, then guess what's true about that triangle? It's a right triangle, okay? So Pythagoras' theorem in the plane is bidirectional. If you have a right triangle, then a squared plus b squared equals c squared. And if you have a triangle for which a squared plus b squared equals c squared, then that triangle is in fact right. Okay, it goes both directions. But not all logical statements are like that. Okay, so what was our good example last time? The lottery, right? If I win the lottery, I will give you each $1,000. You know what? I'll even go further than that. If you win the lottery, I will pay all of your tuition accounts. Guess I'm going to save a little bit on you, huh? Huh?
Thanks.
Yeah. Sorry. Yeah, that's true, right? And it didn't involve playing the lottery. Okay, anyway, so if I win the lottery, I'll pay all of your tuition accounts for all 4 years, right? So what would happen if tomorrow you got a note from the business office that says your tuition for the next 4 years has been paid? You'd be thrilled, but could you conclude that I won the lottery? Well, you probably wouldn't care. Yeah, okay, good point, right? You couldn't conclude that I won the lottery. Maybe, I don't know, some rich alum just decided to pay off your balances. Maybe the college won the lottery. I don't know how that would happen. Um, Maybe I'm just rich and a nice guy. Okay, now we can bet that probably the me being rich, independently wealthy is not true, because if that were the case, would I be teaching? Probably, actually. I'd get bored. Um, yeah, I'd get bored if I weren't teaching. Would I be teaching 3 classes every semester? Hell no. Okay, I'd tone it down a bit. Okay, all right. So don't confuse the two. Is the salient point there? Okay, so what does the series 1/n² do? It converges. Why? Okay, the why is the really important part here. There's multiple acceptable whys in this case. Okay, what is one acceptable why? The p-test. Right, because it's equal to 1. Right, since 2 is bigger than 1, this thing converges by the p-test. Okay? Probably. Yeah, in the basement. Um, so this is the specific case. The p-test for 1/n, p is 1, and that's not bigger than 1. But for n², right, um, yeah, it's like this right there.
Oh.
We've got p equals 2, right? Last time I checked, 2 is bigger than 1. Okay. All right, so this thing converges by the p-test. Could also do the integral test here, but p-test is sufficient. Okay, so all right, so that thing also converges. Now, I'm going to call this the direct comparison theorem, uh, because there's a second comparison theorem that we're going to talk about next that has a different name, and this way it's just easier to keep track of which one we mean. Okay, that's all. All right, so do you guys buy that? Okay, so what's the TLDR? Smaller than a convergent, you converge. Bigger than a divergent, you diverge. But you have to verify that you are, in fact, like that the inequalities go the correct direction, etc. Okay, because if not, then you're going to get garbage. Okay, and the inequalities, by the way, are what I want to talk about next. Okay, so I'll take a just quick breather and let you guys absorb. Um, yeah, that's sort of a rule of thumb, I guess. Yeah. But as we're going to see in a minute, if this +1 had been a -1, this wouldn't have worked. Okay, but there's a solution. Yeah, Donovan. Ah, Yes, okay. Yeah, all right. So good question. So let's say that, okay, so Donovan's question, what about if I had something like that, say? Okay, so what to compare against? Okay, so here's my rule of thumb for these situations where you have oftentimes the series, the thing we're looking at is a rational function, meaning it's some sort of polynomial or algebraic expression in terms of n on top and on bottom. Okay, what is the biggest power of n you see on top? Yeah, just to the first, okay? And what about on the bottom? Okay, so what I'm going to compare against would be the ratio of those things. So I would try 1 over n, okay? And I'm thinking of that as being n over n squared, okay? So that uh, with direct comparison, or especially where this is going to be powerful, is with the next rule or the next theorem, uh, is that you would probably compare it to that. Now, what about if you have something like a square root? Okay, so let's talk that, for example. What about if I had something like, what's the biggest power of n on top? 1/2. What's the biggest power of n on the bottom? Okay, what does it look like the biggest power of n on the bottom is? Looks like it's n squared, but the whole thing is square rooted, so what effectively is it? Just n. Okay, does that make sense, what I mean by effectively? Yeah. Okay, so in this case, I would try that. Okay, so it's essentially the ratio of the biggest powers. No, because what's the biggest power upstairs? Yeah, yeah.
So,
Yeah. But how did I get 1 over root n? I got it by thinking of what's the biggest power of n at the top? Root n. What about the bottom? Root n squared. And what's the ratio of those two things? 1 over root n, right? Okay. And so I want to possibly compare against 1 over root n. Now, um, the thing I don't like about the direct comparison test is it requires that the inequality go in a particular order, right? And a lot of times it goes in that order and everything's cool. But what about if it doesn't? Then what? You still, this comparison or this second thing that I want to compare against, that trick will still work, but what we're going to have to use is a different comparison theorem. Okay, so my go-to, like when I look at a series, and this is something that like you guys will start to develop as you do a bunch of exercises. So let me back up for a moment. Let's think back to when we were doing the integral chapter, right? The techniques chapter. So in Calc 1, you knew two techniques: U substitution and have it memorized, right? And then we gave you integration by parts and partial fractions and trig substitution and all of these crazy methods, right? And then what started to happen? You get a big pile of integrals and you have to suss out which technique is going to be the way to go. Sometimes there's more than one that'll do the job, right? But it's up to you to figure out which technique is a good move. Well, the same thing's going to be true with series, right? Again, we're going to give you a bunch of new theorems, bunch of tools, and part of the challenge for you guys is to suss out which technique is going to be a good move and which one's not going to be a good move. Okay, so my rule of thumb is if you do direct comparison and everything's going great except the inequality is going the wrong direction. Okay, so the alligator is facing the way you don't want it to face. Okay, now you guys get the alligators, right? Yeah. Okay, do you guys did you guys learn about alligators with inequality symbols when you were in school? Well, okay, so you know, 2 is less than 3. The alligator always wants to eat the bigger number. Nom nom, right? That's how, like, I think I was in first or second grade when that was explained that way. Yeah, okay, and I'll never forget it. Okay, so my rule of thumb is if everything's looking good with direct comparison, except the dang alligator's facing the wrong way, then try this other kind of comparison instead. This other kind of comparison, which I'm about to write up, is called limit comparison. Okay, so okay, so here I've got two non-negative sequences A-n and B-n, and I'm not going to worry about which one is bigger than the other. I don't actually care. What I care about is what happens to their ratio. I'm going to take their ratio and I'm going to take the limit of that thing as n goes to infinity. Okay, and I'm going to get something. Okay, what are the possible values that I could get for L? I could get infinity, I could get 0, and I could get anything in between. Okay, so those are going to be the three cases that we need to consider. L equals infinity, L equals 0, and L equals a non-zero constant. Okay? All right, does that make sense that well, first off, that those are the only three possible situations? How do I know that L can't be a negative number? Yeah, because what's true about the two sequences? They're non-negative, right? I'm not going to get a negative limit out of two non-negative things. Like, that just ain't happening. Okay, Gucci? All right, so the first result here, I'll take the case where that limit is some positive number, but it's not infinity and it's not 0. It's somewhere in between. Then they either both converge or they both diverge. Okay, so now remember, in practice, you are the one choosing the B sub n sequence. Okay, and so choose wisely, but that's half the game, is not only realizing, hey, comparison is going to be a good technique here, but what should I compare against? And that's where Donovan's question actually gives us a lot of ammunition. It's not always going to be the case that I would do that. And as you guys work exercises, you're going to start to get the spidey sense for what techniques to deploy when. That will come with practice. Okay. All right. So that's case 1. Case 2 and 3 are less commonly used in practice, but they come up enough that it's worth talking about. Okay. So what's the next case? Let's do the case of L equals 0. Okay, so kind of the way to think about this is if that limit is 0, then in a sense, the sequence B sub n like ultra dominates the sequence A sub n. Okay, and if it does, then and the B sub n series converges, then the A sub n series converging is perhaps not a huge surprise. Okay, now I haven't proved this, but like just from an intuition standpoint, this seems reasonable. Okay, but notice that this one requires 2 things. It's not good enough that L equals 0. It has to be L equals 0 and the B sub n series converges. Then you get the other one converging too. Okay, and what's the order here? The B sub n sequence is always the dude in the denominator. Okay. All right, so that's case 2. What would case 3 be? L equals, right? Wait a minute, do I have that right? Hold on 1 second.
Well, for case 2, wouldn't B sub n have to diverge because then you'd have a constant over infinity to make it 0?
No, because it's not saying that A sub n limit is a constant. It's saying that the limit of the ratio is a constant. They're not the same thing. I may not be understanding your question correctly. Oh, yeah. This should be B sub n, sorry. Oh, yeah, and I guess that makes sense, right? So the second or the third case, right, is if you've got an infinite ratio and the B sub n series diverges, the ratio being infinite to some extent says that the sequence A sub n super dominates the sequence B sub n. And if the B sub n series diverges, then the A sub n one would diverge also. Okay, case 1 is, I think, the one that in practice you probably use the most. And case 2 and 3, less common, but they come up enough that it's worth talking about. Okay, so here's my handy dandy rule of thumb. When I look at something and I say, you know what, comparison's going to be the way to go, the first thing I try is direct comparison. And if everything's working out except for the dang inequality, just use the same B sub n and try limit comparison instead. And 99 times out of 100, that'll do the job. Okay. Now, what's a good idea for what to compare against? That was Donovan's question, right? And so what was my trick there? Yeah, the ratio of the biggest powers of n that you see. A lot of the time is going to do the job for you, okay? Now, it's not the only situation that could come up, but in practice, that's usually going to be a good move. All right, we should quit. It's we're a couple minutes over. Thanks for playing. Hope you guys had fun. I will see you guys on Wednesday.